Bismillahirrahmanirrahim. Welcome to Linear System Homework 6. You're having a question. It's inverted pendulum. And we are having a cart and inverted pendulum. This is the inverted pendulum model. And here this is the capital M is the mass of the cart, small m is the mass of the inverted pendulum, this rod. Similarly, L is the length of this rod, and I is the moment of inertia. This is the state space form. The inverted pendulum system is given in the state space form. This is the x dot ax plus bu. So this is the A matrix, system matrix. This is the input matrix. When this is the C is the output matrix. And we are having the state vector given as x is equal to theta angular position, theta dot angular velocity, angular position of angular displacement by the cart, and z dot is the x and the linear displacement of the cart. So z is the linear displacement of the cart and z dot is the linear velocity of the cart. You have to, in the first instance, we have to check the B stability of the given system. Similarly, we are having the part B says the initial velocity and displacement of the cart is 0, initial angle of the pendulum is 0.02, and angular velocity is equal to 0. Design amazing controller discussed in the class. So this is the amazing controller UA. This is minus BT e to power A transpose. This is the relationship for the amazing controller, and we are having the Gramian controllability Gramian W. This is the relationship for the Gramian, and we are here we can calculate the controllability Gramian numerically. So this is the code in the MATLAB. Similarly, the part C says use the controllability matrix, which is the controllability of the system matrix, and D says that use the Ackermann's formula for the pole placement of this system. We are having the zeta that is equal to 0.707, the damping ratio, and the natural frequency omega n is equal to 7.07, and the time for this is the t0 to 2.5. This is the simulation time. So here in the first case we are having this system. We are checking the B stability of the given system. So we are having we can check the B stability for if we are having the transfer function that is equal to g of a is equal to c s I minus a. This is the inverse and B. And if we calculate the g of s, the denominator as the characteristics for polynomial, and if we put the characteristics polynomial equal to 0, that will become the characteristics equation. And by finding the characteristics equation, the value comes out to be s equal to 0, 0, minus 2, 1, 2.11. So as one of the pole is positive of the characteristics equation of which is the root of this characteristic equation, so hence the system is Bibo unstable. Since this is the MATLAB code, we are having the A matrix, B matrix, C matrix, and we have calculated the roots of the characteristics equation. This is the characteristics polynomial determinant Si minus A. Alternatively, we can also calculate the determinant of lambda I minus A, and that will be the poles of this system. So if any pole is equal to positive, so it will be the system will be unstable. Alternatively, we are having a pole if the eigenvalues of the system matrix A, if any value of the system matrix A is positive, so the system will be unstable. So these are the values. Now coming to the question number part B, we are having the vector is giving, we are having the state vectors theta dot z and z dot from the initial condition. So this is the initial condition over here. So here in this case this is not equal to 0.02. basically here this is equal to the x naught is equal to 0.02. so this is a small mistake, type of mistake. The initial condition for the theta that is equal to 0.02 radians. So by amazing controller UA, we are having this system. We are simulating this problem for 2 seconds, and this is the system matrix A, this is B, this is C, and this is the initial condition here. This is the rightly placed here, and now t1 is equal to 2 seconds. Now we calculate the time that should go from the 0 to t1, which is equal to 2 seconds. In this case, this is the W, the controllability Gramian. This is the U, A, this is the vector defined here. And similarly, the UA is we can calculate it to a recomputation of the control input here. This is the given the relationship, and we are numerically calculating it over here. Similarly, we are having the system, and this is the open loop system. This is the state space model of the system, and by using the lsim command, we are having the UA over here. That is the amazing controller, and we are having this is the time, and this is the initial condition. So based on this, we are having this is the y output. So we can in the first place we can plot t versus the amazing controller, and which is the open loop response, which shows the actuator. And in the second case, we can also plot the response of the multiple responses of the output, like the angular position, angular velocity of the pendulum, angular the linear displacement, and linear velocity of the cart. So these are the y1, y2, y3, and y4. These all are so here. This is the in the first case, this is the UA for the this actuator force for the UA amazing controller. We are having this is the amplitude, this is the time, and similarly this is the response of also for the 2 second we have simulated the system, and all the response go to 0. So this is the response of the this is the open loop response. Now this is the Simulink model implementation. We are having from the workspace we have to put that value equal to the UA value here, and this is the state space model. We are having the scope, and we can alternatively represent that is the output responses, the angular angular response of the pendulum, and the linear response of the linear response of the card. Similarly, this is the actuator force, which is driving this the amazing controller force, which is driving this all these responses equal to 0 for 2 seconds. So this is the 2 seconds here in the Simulink model. So this is the Simulink model. Similarly, in the part C, that it is asked to use the controllability matrix to check the controllability of the system used. So we can check the controllability. We are having the full rank matrix, like this is the aim in this case is the controllability matrix, that is equal to B A B A square B and A cube B. So if the control C controllability of this the matrix is equal to the rank of this matrix is equal to this full rank matrix, so it will be controllable. It means if these the controllability, the rank of this matrix is equal to 4, that it means that we are having 4 linear independent rows or 4 linear independent columns. So alternate we have also shown this here. This is a 4 by 4 matrix, and so the system is controllable. Now the D part says that we are having the damping ratio that is given 0.707, omega n is also given 7.07. The time is asked to simulate the system from 0 to 2.5, and these are the closed loop the poles. So by using the Ackermann's formula, which is equal to in the MATLAB, that is equal to K is equal to AC KER AB, and these are the pole position -5 -5A, and here this is the and -20. So we are having a pole pair, complex pole pair over here, and here this is the -20, 2 poles lie over here, and these are the real poles and the real negative poles. So this is the characteristic equation in the MATLAB. S is equal to, similarly we can write that is equal to AB minus 5, that is a closed loop A minus BK. So this is the closed loop system, and this is the pole placement method. So we are having a state space model, the closed loop model of the state space, and we are having this time to up to 2.5 second, where this is the initial response x naught, and we are having figures. So this is the value of the gain key which is calculated, and these are the responses of the this is a closed loop response of the system when we consider the pole placement by using the Ackermann's formula. Similarly, we can also show in Simulink the state space model in Simulink, in which it shows that this is the theta, this is the theta dot, the red one, and the card position shown by this is the yellow. And similarly we are having this position, this is the position of the cart velocity. So this is the Simulink implementation. Part E asks that perform the for a time t equal to 0 to 2.5, plot the cart displacement from the part B and D together. So we are having the code is given for this, for in which the open loop system, in the first instance we are having the closed loop system, in the second part we are having the open loop system, and the combined graph is drawn over here. So in this graph we can this is the closed loop system we are having, this one, and this is the brown one is the open loop system, and this is the cart displacement. So it shows that for the open loop system we are having there are some oscillations, and the response goes to 0 at 2.5. so nearly 2.5 second it's almost dragging the cart is going towards the 0 position. But for the pole placement we are having this is the required response by arbitrarily choosing the position of the poles, so according to our own choice. So this is the here in this second case for 2.5 we are having this is the control force for the amazing control actuator. So with this I conclude this presentation. Thank you.